In this video, we are going to show you why we need to apply dynamic frequency scaling DFS on the fly to maximize SoC bandwidth. Before talking about the DFS, let's review the two-dimensional DVFS image, which would have a different scenario. For example, you may use lots of applications on your mobile device to fulfill your aggressive request. The device or SoC must operate in a high power mode with a very high clock frequency or high data rate, but burning lots of power. Once you stop heavily using your device, the SoC may detect only little applications running on your mobile device, and then switch to the low clock frequency or low data rate with a low power operation. Clearly, the DVFS is a method we have the flexibility to adjust the voltage and frequency to fulfill low power or high speed system requirements dynamically. In reality, the supply voltage is not constant. Could you please think of the supply profile images for 5 seconds? Correct. The power supply can dip quite a bit. For example, in 5nm SoC, there are 8.5 billion transistors. A reset state of a few memories or several processor cores will start at the same time to cause rapid increase in supply current, and then the package and PCB inductance results in fast supply drops. In the DVFS video, we were aware a low supply voltage would have a less timing margin to likely violate the timing. Is the power supply the only impaired image in the digital circuit? Of course not. Besides the supply voltage, we know both process and temperature also have a big impact on the digital speed. Therefore, any designer must verify your circuit block over PVT conditions and conclude a worst-case performance to be your final circuit performance. The logic delay images show you how the digital gate speed varies with P, V, and T. The variation is gigantic, 2.5 times over normal voltage range, or up to 10 times over the extended range commonly used in modern SoC and especially in high-performance compute chips and AI accelerators. Because we must meet the logic timing for the worst case, most chips in production are performing well below their potential speed. We show the supply voltage on the horizontal axis of the tables, and it's obvious the voltage effect dominates. This means that even the chips are being into fast parts and slow parts, and the supply voltage is adjusted accordingly. The dynamic change in the supply voltage must be accounted for by allowing more timing margins. If we can adjust the clock rate as the power supply level changes, the chip can run faster when the supply is high and slower when the supply drops. Let's summarize the difference between the DFS and DVFS one more time. The need for the DFS is to maximize the SoC bandwidth by mitigating the supply dip with the dynamic frequency scaling DFS approach, such that most of the time the chips can run faster when the supply is high and slower when the supply drops. On the other hand, the application of the DVFS is to save power while it's not needed and to run faster if needed. Therefore, both voltage and frequency scaling is decided by design. But the supply voltage of the DFS came from the supply profile of a real operation, which was not decided by the system control. So, what is the design requirement of the DFS? Think about the recent image for 5 seconds. Bingo! Faster detection and fast response of the DFS is a must. Otherwise, the timing variation will occur. For example, we must detect the supply dip quickly and then decrease the frequency quickly through a DFS before increase the delay variance, the digital timing. For the supply voltage dip detection, we can apply a simple comparator or ADC like analog voltage level detection, which usually should achieve a quick response compared to the supply dip. Therefore, no matter the DFS or DVFS, the most challenging one would be the faster frequency hopping from one voltage frequency pair to another voltage frequency pair. If the frequency hopping of the clock generator is not fast, what can we do to avoid the timing variation? Think about the standby images for 5 seconds. Correct. The simplest way to avoid timing variation is to halt the system during the transition. In digital clocking, the supply drops can cause timing failures because the uneven slowdown between the clock and data paths. Therefore, we may halt the system before the transition happens if we quickly detect the supply glitches. Then, wait for the clock to lock to the new frequency and settle down such that we can restart the system. Is this system halt a good solution? Of course not. The system's halt degrades the performance because of the long waiting time. To work around the performance penalty, we must leave the system always running. But would that create another issue if we make the frequency hopping too faster? Think about the damping factor images for 5 seconds. Bingo! The second order PL would have a big overshoot if we try to speed up the settling time with a very little damping factor. While the supply dip occurs, the overshoot at the low frequency would not have a timing issue. But while the supply recovers, the overshoot that occurs from a low frequency to a higher frequency hopping would cause a timing issue. What can we do to mitigate the overshoot issue? Think about the DVFS image for 5 seconds. Great. Is this a good problem-solving exercise? Hope you enjoy it. To make the system tolerate the overshoot, we can increase the minimum operating voltage by delta V such that the delay is shorter and can meet the original timing design with extra margin. The original voltage frequency pair target was V2 F2, and the new target with the frequency overshoot is V2 plus delta V2 F2. Does this additional voltage amount bother you? Yes, the increased voltage would not cause higher power, but also have aging reliability concern. If you don't like the overshoot, what else can you do? Again, think about the damping factor image for 5 seconds. Bingo! We can increase the damping factor opacity to eliminate the overshoot, but the lag time will be longer, not fast enough. Therefore, we circle back to the need for the system halt. Looks like we cannot have a faster frequency hopping solution with the closed loop second order or higher order PL. Any idea? Perhaps think about an open loop image for 5 seconds. Correct. We need a first order open loop frequency hopping frequency lock loop FL to achieve fast frequency switching on the fly with no overshoot. Since the frequency must be stable, we still need a lock PL as the main clock generator, but take a copy of the locked PL VCO as a replica and scale. This provides the second output, which is frequency locked to a fractional multiple of the reference clock. For example, we can program the output frequency over a 2.5 to 1 frequency range before an asynchronous output divider. The VCO controlled digital to analog converter DAC is designed to be asynchronously programmed and settle quickly without overshoot. While PLs initially settle on timescale of microseconds, and because they are higher order loops, they either overshoot or settle slowly. The replica VCO with DAC does not overshoot at all and settle on a timescale of tens of nanoseconds. This FFO enables DFS with more timing margin and with frequency change 50 times to 100 times faster than before. The frequency switching even could be fast enough to detect a supply glitch and decrease the large clock frequency ahead of the supply drop. Is the FFO too good to be true? Think about the replica images for 5 seconds. Right, as we all know, transistors in the modern advanced technology does not match very well. This means the output of the VCO2 will not be perfectly on target. In this design, the copy can have a frequency error of 2%. To deal with this, we have added a slow digital calibration loop that adjusts the DAC control word so that the actual ratio of the two VCO output frequency matches the program ratio. Once this calibrated is complete, the calibrated DAC control word can be read out, stored in a lookup table in a non-variant memory, and used for future transition to the same frequency. With a 1-point calibration, the initial error on the frequency jumps is below 0.5%, and with multiple calibration points can be better than 0.01%. We can perform this calibration at a production test or at the first boot of the system. Since our FFO sequence is so promising, I'd like to share with you our 5nm sequence measurement of the time domain frequency hopping behavior. The two images show some measurements with the DAC program to have the output switching from 1.6 GHz to 3.2 GHz and back. You can see the output clock divide down to 800 MHz to get it off chip. Transition rapidly and smoothly to the target frequency without glitches or overshoot. The steps are an artifact of updating the frequency after each clock period measured. The equivalent time constant we measure here is around 7 nanoseconds. As I mentioned in the two slides ahead, the 7 nanosecond hopping time is likely faster than the supply drop in a chip with a several on-chip decoupling. Here are the summarized images of why we need to apply dynamic frequency scaling DFS on the fly to maximize SoC bandwidth. The logic delay over PVT shows you the digital gates speed varies with P, V, and T up to 10 times over the extended range commonly used in modern SoC and especially in HP compute chips and AI accelerators. Since we must meet the logic timing for the worst case, most chips in production are performing well below the potential speed. In addition, the supply voltage dominates the big variation. Even though chips are being into fast parts and small parts, and on-die temperature varies slowly, we must account for the dynamic change in the supply voltage by allowing more timing margin. Since the power supply can dip quite a bit in a big SoC. For example, there are 8.5 billion transistors in a 5nm SoC. Several processors cores may start at the same time to cause rapid increase in supply current, and then both the package and PCB inductance result in a fast supply drops. Therefore, we may need the DFS to maximize the SoC bandwidth by mitigating the supply dip with the dynamic frequency scaling DFS approach, such that most of the time the chip can run faster when the supply is high and slower when the supply drops. Faster detection and faster response of a DFS are requirements to avoid the possibility of timing variation. We can apply a simple comparator or ADC like analog voltage level detection for the supply voltage dip detection easily, but the fast frequency hopping from one voltage frequency pair to another voltage frequency pair could be the most difficult one because of several reasons. First, the system must always run without a system health, and we must change the frequency on the fly. Second, we should not have any frequency overshoot. Lastly, the lag time must be fast compared to the supply drop to avoid timing variation. The traditional PLs with higher order loops either have an overshoot or settle slowly, but we could have another Replica VCO and DAC that does not overshoot at all and settle on a timescale of nanoseconds. With proper power calibration, our 5nm FFOC current measurement of the time domain frequency hopping behavior show you the output frequencies switch from 1.6 GHz to 3.2 GHz and come back without glitches or overshoot in just around 7 nanosecond time constant, which is likely faster than a supply drop in a chip with a reasonable on-die decoupling. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.